everybody, welcome to Combinations with me. This time we are going to be counting objects when order doesn't matter. Remember last time we talked about permutations and that was all about when order mattered. This time, combinations, order doesn't matter. Saying that a little bit more formally, we've got a K combination of elements from a set is an unordered selection, so we don't care about order, of those K elements from that set. Or rephrasing it, we want to count the number of ways we can arrange K many of n total things when order is not important. So remember from last time, we did a 2-digit number from the set 1, 2, 3, 4, 5. Order really mattered there because 23 is not the same thing as 32. However, I'm going to ask, well, what if we just did a 2-element set? Now you've got, like, if we think about 2 and 3, that is the same thing as 3 and 2. Because we don't care about order when we're talking about sets. So I'm going to say, well, I know how to count these guys. I know how to count double-digit numbers, and that's like kind of the same thing as sets because you're still picking 2 numbers. So this guy would be a combo because order is not going to matter. This guy is a permutation because order does matter, and I'm going to use the permutation guide to figure out how many combinations I have. So I know how many permutations I have. That was like the P52. And then I can see from this that we are double counting everything. So when I pick 2, I have 2 ways to arrange them. And so everything is going to be counted twice when we're thinking about combinations. Here we get 2, here we get 1. So if I just divide the number of permutations that I had in half, that's 20 over 2, we get 10 combinations. We're going to use this exact reasoning now to prove a more generalized result. In general, if you want to count the number of K combinations, we have this formula here. Notice that we could rewrite it as like 1 over K factorial times this term and this term, which is our permutation. So let's think about why this theorem is going to work. So if we try and prove this, I'm going to say the number of K of n permutations, so that means we're picking K of n elements, is going to be equal to the number of combinations, so K of n combos. But remember, those K elements that we're picking for each combination, each time we pick a combination, we have a permutation. We have a variety of ways to arrange it. Remember, we've overcounted in the permutation because order matters. So like over here, I said I have this many ways to arrange each of my sets of 2. Same thing over here. We're going to say they are related. My permutation is related to my combination by multiplying my combination, so like K of K permutations. So you get a combination of things, or a combination of elements, and then you can get up to all the permutations if you just do every permutation of that particular combination. Just like right here. That was a combination, and then if I did every permutation of this particular combination, we can go through pair by pair and get up to all of the permutations. So then if we translate this back into formulas, we know what K of n permutations, so K many of n, that was the nk permutation counter. And then this is just the nk combination counter. But then this one is going to be kk for our permutations. And then this guy is known, this guy is known. So we can just solve for our combinations. So we have P of nk over pkk, where the pkk is just how much overcounting was done. That's all that term means. So then that turns into n factorial over n minus k factorial, and then that's over k factorial over k minus k factorial, which remember 0 factorial is just 1. So this is n factorial over k factorial times n minus k factorial. All right, let's take this for a run. Let's just work with the same example that we just had. How many 2-element sets can you make from the set of numbers 1 through 5? We don't care about orders because we are talking about sets. It's like buried information, and so I had to think very carefully, do I care about orders? Should I be using combinations or permutations right now? Order doesn't matter, so I'm using a combination. So n is the total number of elements we're talking about, which is 5. K is like the number of elements that we want to look at arranging, which is 2 of them. So we put that together. And now we have a 5 factorial over 2 factorial, 5 minus 2 factorial, 5 factorial over 2 times 3 factorial, which is equal to, remember this is going to turn into a 5 times 4 if we cancel with the 3 factorial a little bit, is exactly what we got before. Boop. So 10. Let's take this for another try. I've got another example that we actually saw before. Remember when we were drawing cards? And I was just like, oh man, we weren't careful because like I said distinct hand. It doesn't matter if you're holding a queen of hearts and then a king of hearts, or a king of hearts, then a queen of hearts. Like, it's the same hand as far as poker is concerned. So how many distinct hands of 5 cards can you draw from a standard deck of 52? That means I'm asking for distinct hands. Like, we don't care about the order these things are sitting in your hand. Don't care at all. So we're in the land of combinations. Combination of what? So we have 52 total things that we could draw, or cards. We are allowed to have 5 of them in our hands. So we're doing combination of 52 and 5, not a permutation, because again, the order of cards in your hands doesn't matter. That's 52 factorial over 5 factorial, 52 minus 5 factorial, which is, go ahead and flip back to the math that I did. If you simplify this, it's going to be 5 factorial, 47 factorial. Oops. So simplifying this guy specifically, you get 52, 51, 53, or 50, 49. 49 and 48 over 5 factorial. Flip back to lecture 1 for combinatorics. You're going to see that's the number that came up when I was discussing how to do this using like division rule and product rule by themselves. And then it's 2, 5, 9, 8, 9, 6, 0. Same number. Let's do this again for 47 cards. Like, guess if you're allowed to draw 47 cards, how many combinations can you get? So n is 52. K is 5. C, 52. Oh, not 5. We're talking about 47 now. 47, which is 52 factorial over 47 factorial. 52 minus 47 factorial. So 47 factorial times 5 factorial under 52 factorial. Does that look familiar? Fun fact, that is not a coincidence. And you're going to prove that that holds in general. So like if you're doing a combination where like k and n minus k are going to give you the same results because you have both of those factorials sitting there in the denominator. It's a little bit of algebra pushing around, nothing too intense. But yeah, that's a really cool fact. So again, just to really drive home the difference between permutation and combination. Permutations, that would be like performing tasks in a specific order. We care about order. Combination, you can perform some tasks, but it doesn't really matter what order you do them in. So maybe you have to like do the dishes and take out recycle. It doesn't really matter which one you do first. But if you think about like eating dinner and brushing your teeth, now maybe the order matters. Maybe we want to brush our teeth after we eat dinner. So next sort of things that you might encounter for like permutation versus commutation or combination, we could arrange objects like into lines or into sequences. The equivalent for combinations would be just grouping things together. So things don't matter when it's being grouped. That would be like a set. Arranging objects in lines or sequences, that would be things like numbers, 23 versus 32, not the same number. The last thing that we have is we have counting distinguishable arrangements. So again, order is going to matter. If you move what order things are in, so like first place versus second place, that matters, versus counting indistinguishable arrangements where order no longer matters. And then here's our permutation formula and our combination formula, where it is very closely related, but we've used division rule to account for, so accounting for over counting. And that's what that term does. But other than that, that wraps up what I have to talk about for combinations. Again, when you're going through like homework problems or something, you need to always ask yourself, does the order matter? Because that's going to tell you whether or not you're trying to deal with counting something that's a permutation versus if you're counting something that is a combination. Okay, I think I've harped on that enough. I think you guys get it at this point. Anyway, see you guys next time.